so I think that's.
Yeah, I'll switch off the video, otherwise.
Yeah, please, yeah.
So it is indeed live now.
Fine. Okay. But I don't see it. I'm also connected to YouTube, but I can't see it. So
It is online, yeah.
online, yes.
You can start actually.
Yeah, we can start. Okay. Fine. It's a great pleasure to have with us Professor Robert Brandenberger from McGill. He is currently Canadian Research Chair in Cosmology and Professor of Physics in McGill. He is a leading expert in early universe cosmology and cosmological inflation. So any serious student in cosmology would have read his review with Mukhanov and Feldman on cosmological perturbation theory, which is considered a classic in this area. He did his PhD at Harvard and did postdocs at Department of Applied Mathematics and Theoretical Physics in Cambridge, and then University of California, Santa Barbara. Until 2004, he was a faculty member at Brown, and from 2004, he moved to McGill, and he's there right now. He has graduated more than 35 PhD students, I think several postdocs. So today he's going to talk to us about cosmological inflation and fundamental physics. So since this is an online talk, I just want to request everybody to mute who are all in Zoom. Professor Brandenberger has agreed to have 2 breaks in between the talk, whichever he finds it convenient. So we will have, that will be like a question answer break. So roughly 20 to 25 minutes will be the first break. So during the breaks, people in the Zoom can ask questions. And anybody who is in the Zoom YouTube audience can pose the questions, and then I will, I am the host, my name is Shankar. I will ask the questions directly to Professor Brandenberger. So now I'll open it to Professor Brandenberger.
Right, so thank you very much for the invitation to speak. And it's amazing to be able to visit Mumbai, Pune, and Bangalore, and maybe other places right at the same time, thanks to electronics. So I'm going to give a talk on inflationary cosmology. I'm going to ask the question whether inflation is consistent with fundamental physics. And if you see a title with a question mark, then you probably should assume that the answer is going to be no, or probably not. And this is indeed the point that I'm going to argue. But I'm going to start fairly slow. I'll give an introduction to early universe cosmology, where we stand. After that, there'll be the first break for questions. Then I'll give a brief review of the simple idea of inflation. And after that, I'll talk about 2 different types of problems for the inflationary scenario. One line of attack comes from superstring theory, and this goes under the name of the Swampland Criteria. And the other line of attack is more closely related to quantum gravity considerations like those put forward by Penrose. This is called the Trans-Planckian censorship conjecture. This is actually quite new. And then I will end, discuss, and conclude. So before 1980, the paradigm of early universe cosmology was nice and simple and self-consistent. The assumptions were threefold. Firstly, was the assumption that space and time is described by Einstein's theory of general relativity. It's a classical physics theory. And matter in this theory is described by the classical matter which we see when we look at the sky, namely a combination of cold matter, pressureless matter, P is pressure, and radiation. Pressure is 1/3 energy density. So the radiation we see in the microwave background, the cold matter is the stuff that we see in terms of the matter that causes light to be lensed. So the third assumption is that space is homogeneous and isotropic, the cosmological principle. So These assumptions lead to the fact that the space-time metric takes a very simple form. And hopefully you can see my cursor. So the line element, which gives the proper distance of space-time, is given this simple form. T is physical time. X, they are the coordinates, the spatial coordinates, which expand as space expands. And A of t, called the scale factor, tells us the size of space. So this is a nice, self-consistent classical theory. And in fact, it had a number of spectacular successes. It explained the observations by Hubble and Lemaitre that space is expanding. It predicted the existence and black body nature of the cosmic microwave background. And it also explained the abundances of light elements. So I have a couple of slides to show each of these. So here you see some data on the Hubble expansion. So redshift, distance, a linear relationship, which is characteristic of an expanding universe. That tells us that if we go back in time, so here the horizontal axis is time, we are here observing the universe with satellites. We go back in time, the universe gets smaller, hotter. Eventually there's the big bang. So if we now move forwards from the time of the Big Bang, near the Big Bang, the universe is a plasma, but eventually the plasma cools to the time when atoms can form. And at that time, photons are released and can free stream to us. And this is a time of recombination. And this explains the origin of this cosmic microwave background. So this is a projection of the sky onto the plane, like a projection of the surface of the Earth. And here you see different temperatures in different directions in the sky. So you see the temperature scale, which runs from 0 degrees to 3.6 degrees Kelvin, not 36 degrees centigrade, as it probably is in Bombay right now. So 3.6 degrees is even cold by Montreal winter standards. And here you see that there's this beautiful isotopy of the microwave background. So the existence of the microwave background is explained, was predicted by standard Big Bang cosmology. And this plot is a spectacular plot. It shows at a given point in the sky, the intensity distribution of the microwave background. So this vertical axis is intensity, horizontal axis is wavelength. And this is actually the observed curve, including the error bars. It's a perfect fit to black body. So these are rather spectacular successes of standard Big Bang cosmology. Standard Big Bang cosmology also explains the abundances of the light elements helium, deuterium, and lithium. So there's one free parameter, namely the ratio of the energy density in regular matter divided by the energy density of photons. So there's a parameter that you can tune, but you see that you can fit all these 3 different observations in one given range of this uncertainty parameter. So these were the successes of standard Big Bang cosmology, but standard Big Bang cosmology left a lot of things unanswered. There was no explanation for the large size and entropy of the universe, no explanation for the observed spatial flatness, no observed explanation for the isotopy of the microwave background, and no explanation for the origin of structure. And in addition, there's an initial singularity. So again, although the standard Big Bang cosmology predicts the existence of a microwave background, it doesn't predict this isotopy. And to show that, I show this slide. Here, the horizontal axis is space, the vertical axis is time. This is a Big Bang. This is the time of recombination. This is the present time. And we look when we look at the microwave background in opposite directions in the sky, we are sort of following the blue line back, the red line back. And the problem for standard Big Bang cosmology is that the region which could have influenced the temperature here has no overlap with the region which could have influenced the temperature here. So there's no way to give the region B the same temperature as region A. So the isotropy of the microwave background is not explained. So what is not explained either is the origin of these fluctuations in the microwave background temperature. So here we've subtracted the monopole, and here we plot anisotropies of the order 10 to the minus 4 Kelvin. So we have hot spots and cold spots in the microwave background. They have, so we can expand this map in spherical harmonics. We can plot the power in different spherical harmonics. So this is the power. This is the different spherical harmonics corresponding to different angular sizes. And the black dots are the quantification of this map. So we have beautiful quantitative data about the distribution of microwave anisotropies, and none of that can be explained with standard Big Bang cosmology. Now, if there are undergraduate students in the audience, a challenge for you is to find out where I'm aligned to you at this point. And you can't use high-tech tools to find the answer, because you won't find the answer. Because all the textbooks say the same thing that I'm going to say now. So this is the structure formation problem illustrated. This is time, the vertical axis, the horizontal axis is space. The co-moving coordinates, coordinates which expand as the universe expands. This line here, the diagonal line, is the standard Big Bang horizon. So the zone of causal influence from a point at the initial surface. This is a time of equal matter and radiation when structures inhomogeneities can start to grow. And today we see inhomogeneities on large scales, on scales which correspond, for example, to this peak. And these scales are actually larger than the horizon at the time of equal matter and radiation. And so you see that this scale is larger than the horizon at equal matter and radiation. And so therefore there's no causal way to be able to explain non-random structure on this scale. Good, so these are some of the problems. So how can we address these problems? Well, we have to go back and replace standard Big Bang cosmology by a different scenario in the very early universe. And here I introduce one more parameter, namely the Hubble expansion rate, which is simply A dot over A, where A is the scale factor. Okay, so first of all, a historical question. Who first predicted this red curve, which fits the data fairly well? And many of you, in particular those of you who've studied cosmology, might be inclined to say, well, it was the people who invented inflation. But this is actually not true. This red curve was predicted 10 years before inflation. It was predicted by Peebles and Yu, and independently by Zeldovich and Zunyaev. And here I have a figure from the 1969-1970 paper by Zunyaev and Zeldovich. So here, the vertical axis is time. The horizontal axis is my co-moving coordinates. This line is a standard Big Bang horizon. This is the time of recombination when the microwave background photons can start to stream freely. Now, what these authors knew is that inhomogeneities are frozen in when the wavelength of these inhomogeneities is larger than the horizon in the radiation phase, or I should say before recombination. But once the wavelength becomes smaller than the horizon, then the fluctuations can start to oscillate. Now, these authors postulated that there is a spectrum of primordial standing wave fluctuations left over from the very early universe. And as you see here, different wavelengths enter the horizon, cross the horizon at different times. So this wave number enters right at recombination, and it enters as a standing wave with maximal deflection. This wave that enters here has had time to do 1/4 of an oscillation. So now you have, it enters as a wave with minimum deflection, maximal velocity, and so on. And from this picture, the prediction was that you will get these acoustic oscillations in the CMB angular power spectrum this year. So you need to fit 6 parameters in order to get the height right, the position right, and maybe the height of these peaks right. But these are the same 6 parameters which are being fitted today. So this is these are the people who first predicted these these acoustic oscillations in the angular power spectrum of the cosmic microwave background. Now, the plot by Zeldovich and Zunayev had a second part, and this is the second part. And the second part shows the matter power spectrum, so the amplitude of the matter fluctuations as a function of wavelength. And the same mechanism that causes the fluctuations to oscillate gives rise to oscillations in the amplitude of the matter power spectrum. And these are the so-called baryon acoustic oscillations, which were discovered, I think, at the turn of the century. So, predictions from 10 years before inflation is acoustic oscillations in the CMB angular power spectrum, baryon acoustic oscillations in the matter power spectrum. So we do not need inflation to reproduce this data. But the one question which was not addressed by these authors is, how does one obtain such a spectrum? A spectrum of super-horizon fluctuations, standing wave fluctuations. And indeed, inflation is the first scenario based on causal physics which yields such a spectrum, but it is not the only one. So what do we need in order to have a successful early universe scenario? So first of all, the horizon, which is the forward light cone of a point on the initial Cauchy surface, has to become much bigger than the horizon that we infer in standard Big Bang cosmology. So the horizon is defined as forward light cone of a point on the initial Cauchy surface. The horizon carries with it causal information, but there's a second quantity, which is the inverse expansion rate. This is called the Hubble radius. And this has an important meaning because it is relevant for the dynamics of the inhomogeneities. Inhomogeneities oscillate on sub-Hubble scales. They are frozen on super-Hubble scales. Now, in standard Big Bang cosmology, the Hubble radius and the horizon are the same, and therefore you have a horizon problem, and therefore you can't explain the ordering of structure. So in any theory which can provide a mechanism for the ordering of structure, the Hubble radius has to be much different from the horizon. The horizon has to be much larger. So this is the first criterion for successful early universe cosmology. Now, if you want to causally explain the origin of structure, then the scales that we observe today have to start out smaller than the Hubble radius. Otherwise, you can't move matter around in order to create fluctuations in a finite time. So that's the second criterion. Now, if you want to start fluctuations in the vacuum state, then you need to have squeezing of fluctuations on super-Hubble scales. And finally, the mechanism should produce a roughly scale invariant spectrum of fluctuations on super-Hubble scales. So this is a statement that says that if you compare the position space fluctuations of the curvature on different wavelengths, you get the same result. That's a scale invariant spectrum of fluctuations. So these are the 4 criteria for successful early universe cosmology. And inflation is indeed one realization which can satisfy these 4 criteria. So this is the space-time diagram of inflation. This is time. This is space. And inflation postulates that there's a period starting at a time t sub I, ending at a time t sub r, during which the universe expands exponentially. Space expands exponentially. So the Hubble radius, which is the inverse expansion rate, is therefore constant during this phase of exponential expansion. But the horizon expands exponentially. So this period of inflation produces the exponentially large deviation of horizon from Hubble radius. Now also this exponential expansion of space, it makes sure that fluctuations that we see today on large scales originate on scales smaller than the Hubble radius at the beginning of inflation. So criterion 2 satisfied. Fluctuations evolve for a long time on super Hubble scales. That gives rise to squeezing. Criterion 3 satisfied. And the time translation invariance in this phase generates, ensures that the amplitude of fluctuations when they exit the Hubble radius is independent of scale. And this means that the 4th criteria is satisfied. So inflation satisfies all 4 criteria. But there are other ways to satisfy the 4 criteria. And this is a space-time sketch of a bouncing cosmology. So in a bouncing cosmology, I assume that the scale factor, as a function of time, evolves in the following way. There's a phase of contraction. Then there's some new physics which generates a transition between contraction and expansion. And then you get standard Big Bang-like expansion. So here's a space-time diagram, time and space. This is the bounce point. This is the contracting phase. This is the expanding phase. Here I draw co-moving coordinates. This line, which is diagonal in the contracting phase, diagonal in the expanding phase, that's the Hubble radius. And these indicate fixed co-moving scales, scales of fluctuations. So time runs from -infinity to +infinity, so the horizon is infinite, infinitely larger than the Hubble radius. Fluctuations start out sub-Hubble in the early universe, early in the contracting phase. Fluctuations propagate for a long time on super-Hubble scales. So the 3 first criteria are satisfied. And the 4th criterion can also now in different models of contraction. I'll come back to that at the very end if I have time. Now, a 3rd class of scenarios are emergent universe scenarios, where you assume that there was a pre-geometric phase where the universe can be viewed as static, so scale factor as a function of time. Then there's a phase transition directly to the standard Big Bang phase of expansion. So that's the assumption that goes into the emergent universe. This is the corresponding space-time diagram. Space, time. This is the phase transition point. The universe is static, therefore the Hubble radius is infinite. The red indicate these physical scales of fluctuations. Fluctuations start out sub-Hubble. They evolve for a long time on super-Hubble scales. And so therefore the first 3 criteria for successful early universe cosmology are satisfied. And if you assume that this early universe phase is a thermal gas of superstrings, then you get a scale invariant spectrum of fluctuations. Okay, so the bottom line of this long introductory section is that we do not need inflation to explain the data, even though it is certainly true that inflation does explain the data. So maybe I'll break for questions here. Any questions?
I think Vikram had a question. Vikram?
Yeah, my question was just about what you meant by squeezing of modes on super horizon scales. What does that term mean? Squeezing.
Okay, this is the same effect that happens in a laser. So if you expand the fluctuations in Fourier modes, and you look at the equation of motion of the Fourier modes, then you get a harmonic oscillator equation with a tachyonic correction to the mass term. And that's the squeezing.
So it's
I can show you later on in terms of equations, maybe at the end of the talk.
Oh, I mean, is it unstable?
Well, it gives rise to the growth of the canonical fluctuation variable.
Okay.
It's not an exponential instability, it's a power law instability. It is the mechanism that in inflation and in a bouncing cosmology ensures that quantum vacuum fluctuations can become large amplitude classical fluctuations.
I mean, for a coherent state, I understand squeezing as a quantum effect, right? Where it's squeezing the uncertainty on, let's say, either the field or its velocity of the field.
That's right. That's what it is. If we start with vacuum fluctuations.
So which way is it getting squeezed?
The amplitude is increased. The velocity, the momentum is decreased.
Okay, thanks.
So it's squeezing in Q direction.
Shanky, can I ask a question? This is Sriram.
Yeah, please.
Robert, you were mentioning that the horizon is infinite in bouncing models.
Yes.
Now, the modes would have left it, cosmological scales would have left at a finite time in the past.
Right, but when we say leaving, it's always crossing the Hubble radius, not the horizon. So see, in cosmology, people usually call the Hubble radius horizon, and that causes lots of confusion.
I understand, but in the sense of, they would have left the Hubble radius in a finite time in the past, and
That's
therefore,
for example, this plot here.
Right. So my question is, we don't need to go, just like in the context of inflation, we need a certain number of E-folds of inflation prior to its end, about 65 or so. In a similar fashion, we need only a certain contracting phase.
That's right. And a certain length of the emergent phase as well. Yes, we don't need the emergent phase to go back to time t equals minus infinity. It only need, it needs, in this setup, it needs to last about 1 second.
Okay. Thank you.
Looks like there's no more question.
Okay, so let me continue.
Please go ahead. Please continue. Thank you.
Right. So now I will start with a brief review of the inflationary scenario. So in the inflationary paradigm, the assumption is, as I indicated earlier, that there is a phase of accelerated, in fact, usually almost exponential expansion. It lasts for a finite amount of time, finite in both directions. So, as I already indicated, this solves some of the problems of the standard Big Bang cosmology, and it provided a causal mechanism for structure formation. But it has an initial singularity. So this is the idea of inflation. And how does one get inflation? So in the usual way of describing inflation, space-time is described by the Einstein action, and matter is dominated in the inflationary phase by a slowly rolling scalar field. So a scalar field, see, with a scalar field, you can get anything you want. So in particular, if you want to get inflation, you can get inflation using a scalar field. So now if you work in the context of the Einstein action, then in order to get almost exponential expansion, you need an equation of state with pressure almost equal to minus the energy density. And if you use a scalar field, then you can get such an equation of state if the scalar field energy is dominated by potential energy. So now, in case there are students in the audience who are not familiar with scalar fields, here is a toy model for a scalar field. So scalar fields are much, much simpler than the electromagnetic field, which I'm sure all of you are familiar with. So imagine a table, and at each point of the table, there's a pencil, which is pinned down at this point X, and it is free to oscillate back and forth. And the angle of the pencil from the vertical is called phi. It depends on the position of the pencil, and it depends on time. And the tips of neighboring pencils are connected by springs. So this is a toy model of a scalar field. Now in this toy model, there are three sources of energy density. There's a kinetic energy when phi is changing. There's a gradient energy. So if the pencils are pointing in different directions, there's an energy cost, that's a gradient energy. And then if this is a laboratory setup, then there's gravity acting, and it means that there's gravitational potential energy. And in particular, if the pencil stands upright, that has a potential energy cost. So for such a scalar field, you have three contributions to the energy density: kinetic energy, tension energy, potential energy. And if it's a relativistic system, then the kinetic energy and the tension energy are related in this special relativistic, in this Lorentz invariant way. But the potential energy is quite free. This is Lagrangian. Based on this Lagrangian, you can also compute the pressure. And you find that this term contributes positively to the pressure. This term contributes negatively to the pressure, but not negatively enough. It doesn't give you acceleration. So in order to get an equation of state which has pressure almost equal to minus energy density, you need to play with this potential energy. You need to have potential energy dominated evolution. So the equation of motion for such a scalar field is this in an expanded universe. And the Slur-Roll condition, the condition that the kinetic energy is subdominant to the potential energy, that implies this condition on the slope of the potential. If the potential is too steep, the field will roll fast and you'll get kinetic energy domination. And this Slur-Roll condition has to last for a long time, and this gives rise to this second condition. So if you give me a scalar field with a potential which satisfies these conditions, I can generate an inflationary trajectory. And if I have a field range which is bigger than m Planck mass, then this inflationary trajectory can even be a local attractor in initial condition space. So this is the way that one gets inflation. Good, so this is a very simple picture. It is based on classical physics. Although it uses scalar fields, it is classical aspects of scalar fields. And this is self-consistent as an effect of field theory. But the question is, does it actually emerge from an ultraviolet complete theory? And this question is going to be the question that I'll address in the rest of the talk. So again, you should keep in mind, I showed you that if you have a scalar field with a potential energy which satisfies these criteria, then it is possible to get inflation. But again, with scalar fields, you can get anything you want. There's a theorem that says, give me a scale factor for the evolution of the universe. You can find a scalar field potential, which gives you that. So if we want to learn something from cosmology, we better make sure that if the early universe is indeed described by inflation, that then inflation emerges from an ultraviolet complete theory. Okay, and now I will argue that there are severe obstacles to obtaining inflation. One set of obstacles come from superstring theory. These are the Swampland conjectures. And the other obstacles come from a generalization of Penrose's cosmic censorship hypothesis. That's the so-called Trans-Planckian censorship conjecture of 2019. Okay, so first I will address the Swampland criteria, and at the end of that discussion, I'll pause again for questions. So, now among many people, among many physicists, string theory has a bad press. Because many people say that, well, with string theory, you can get anything you want. There's so many vacuums, so many fields. Nothing could be further than from the truth. What is true is that if you work at the level of effective field theories involving scalar fields, then there is a huge landscape of effective theories. Any space-time dimension works, any number of fields works, any shape of the potential works, any field range is okay. You can get anything you want. Superstring theory is very constraining. It sets the number of space-time dimensions. It is fixed, 9 + 1. All scalar fields have a stringy origin, a geometric origin. And potentials all arise from string theory. So only a very small subset of all effective field theories are actually consistent with string theory. The rest lie in the swampland. So here's a picture. You have string theory, which is very constraining. Here you have this unconstrained realm of effective field theories, and that only a very small set of islands in this swampland are consistent with string theory. And we should ask the question, what are the conditions on an effective field theory in order to lie in the habitable islands? So what are the conditions for habitable islands to stick out of the swamp? So the first condition is that the field range over which the effective field theory can be trusted cannot be larger than the Planck mass. The second set of criteria refer to the potential. So a potential of a scalar field, which comes from string theory, has to be sufficiently steep or sufficiently tachyonic. So all of these numbers D, C1 and C2 are constants of the order 1. So these are the swampland criteria for scalar field potentials to be consistent with string theory. Okay, so now I am not a string theorist, and so therefore I cannot give you a very good justification for these conjectures. I can only give you a superficial justification. So the field range condition, the superficial justification for that is the following. So phi, the scalar field, is a string theory modulus field. It describes aspects of the 6-dimensional internal space. And now in models where we can do calculations, you find that if you move a distance m Planck in this field space, then you get a huge tower of string states, which previously were high mass, mainly string mass. They become effectively massless, and they must be included in the low energy effective field theory. So the effective field theory will change if you move a distance more than m Planck. So that's the justification for the field range condition. Now, the condition on the potential, you can again justify that in the following way. A field phi coming from string theory is a modulus field. You can visualize it, for example, as the radius of an extra dimension. It is stabilized by string effects. And in models where you can do calculations, you find that the potential which stabilizes a moduli is steep. It's an m square phi square potential. And for an example, you can look at this reference. So this is the stringy origin of these conjectures. So again, it's not theorems, but it's criteria would follow from models where you can do well-defined calculations. Okay, so now let's go back to inflation. You see, first of all, inflation requires large field distances. It requires very low slope and very small second derivative. And you see that these criteria are opposite to all of the criteria that come from string theory. So both the field range and the set of conjecture are inconsistent with this. So therefore you conclude that slow roll inflation is in the swampland, false vacuum inflation is in the swampland. However, not all inflation models on the swampland, for example, worm inflation, it can escape from the swamp because worm inflation is a scenario where you can inflate on a steep potential and you don't need large field ranges. Okay, questions here?
Robert, how does worm inflation avoid the swampland? How does the radiation help?
Okay, let me go back. It is this equation which changes. You have an extra friction term, and if the friction coefficient is large, you can have large gradients. And also you don't need to roll for long distance.
Okay, I understand.
Other questions?
I have a question. So this KKLP model,
Yes.
is it within the swampland or is it outside the swampland?
It is deep, deep, deep in the swampland. And I refer to you to papers by Keshav Dasgupta pointing this out.
Okay. Okay.
This is a controversial statement, by the way.
I know that. That's the reason why I asked you this question. So I keep reading so many contradictory statements here and there. So
That's right. That's right.
okay, fine. Okay.
Right. More questions? Or shall I go on to the second line of attack?
Yeah, you can go ahead, please. Yes.
Okay. Good. So the second line of attack, it originates from work that I did with Jérôme Martin almost 20 years ago. There we pointed out that there's a Trans-Planckian problem for fluctuations in inflationary cosmology. So here you see a space-time diagram, the same space diagram for inflation which you saw before. So vertical axis is time. Inflation is between Ti and T sub r. This is physical distance. The Hubble radius, the blue solid curve. The horizon, which is exponentially larger. The physical wavelength of co-moving fluctuations. And the success of inflation is that this physical wavelength of fluctuations we observe today at the beginning of inflation is smaller than the Hubble radius. But now I added one more line to this graph, namely the Planck length. And now you see from this graph that if the duration of inflation is too long, then this length scale, the length scale of everything that we observe today, even stuff on the largest cosmological scales, starts out smaller than the Planck length at the beginning of inflation. And in this region here, wavelength smaller than the Planck length, we can definitely not use effective field theory. Because quantum gravity will definitely show its head. So we pointed out that if the period of inflation is more than 70 Hubble times, then the physical wavelength of the fluctuations that we see today is smaller than the Planck length at the beginning of inflation, and therefore new physics must enter into the calculation of the fluctuations. So there might be bad stuff happening here, and we need to control this bad stuff in order to really understand the predictions of inflation. But then last summer, based on a talk which I gave on this scenario, Bedroya and Waffe proposed to elevate this into a censorship conjecture. They said that it should not be possible ever for trans-Planckian modes to exit the Hubble horizon. So this is the Trans-Planckian censorship conjecture. No trans-Planckian fluctuation modes ever exit the Hubble horizon. So what does this mean? Let's go back to the framework. Homogeneous and isotropic cosmology. Hubble parameter. The Hubble horizon is H inverse. And the TCC says that if at any early time, T sub I, you start with the Planck length, then the Planck length will never become larger than the Hubble horizon at a later time, T sub R. So this is the mathematical characterization of the TCC. Good. Now, what is the justification for that? And here I will go back. I'll give two different justifications, one of them in analogy with Penrose's cosmic censorship hypothesis. So Penrose was considering black holes. And if you have black holes with charge smaller than the mass, then you have a horizon. So this is the center of the black hole. This is the radial coordinate of an external observer, the external observer. And at the center of the black hole, there's a singularity. But the observer is shielded from this singularity by the horizon. The observer will never see the bad stuff associated with this horizon, as shown by this geodesic. Now, Einstein's equations also admit solutions with charge greater than the mass. So Einstein's equations as an effective field theory admit solutions with Q greater than M. And for those solutions, there is no horizon. There is a singularity, a time-like singularity. This is the radial coordinate. And the poor observer far away from the black hole center will see stuff coming from the singularity. So Penrose hypothesized that even though the effective field theory admits such pathological solutions, the full theory will not. So general relativity as an effective field theory allows for solutions with time-like singularities, but the complete ultraviolet physics will not allow such solutions. The external observer will be shielded from the singularity and non-unitarity by the black hole horizon. So now let's translate this to cosmology. The singularity becomes the Trans-Planckian region of modes. The black hole horizon becomes a Hubble horizon. And so translating this last point will lead you to the conjecture that the observer outside of the Hubble horizon, so the observer who's measuring fluctuations with wavelength larger than the Hubble horizon, this observer must be shielded from Trans-Planckian modes. Good, so now why do we use the Hubble horizon? So the justification for that is the following, and here I refer you to the paper I wrote again with Bedroya, Waffe, and Loverde. So fluctuations oscillate on sub-Hubble scales, and they freeze out, become squeezed, and classicalize on super-Hubble scales. So, well, if there's some strange stuff in the Trans-Planckian region, but it always remains sub-Hubble horizon, it can never grow, and it can never, therefore, influence the observations we make today. So a conservative demand is to demand that the classical region be insensitive to the Trans-Planckian region, classical region, meaning the super Hubble region. So no Trans-Planckian modes ever exit the Hubble horizon. So these were two justifications for this Trans-Planckian cosmic conjecture, censorship conjecture. Okay, so now the other line of justifying the TCC comes from the non-unitarity of quantum field theory in an expanding universe. And there's an old paper by Nathan Weiss, which already makes this point. So when we look at fluctuations in cosmology, we look at linearized fluctuations, we expand the matter fluctuations and metric fluctuations into harmonic oscillator modes. And there's one Hilbert space, one harmonic oscillator Hilbert space for each co-moving wave number. So the Hilbert space is the product Hilbert space of all of the co-moving modes, mode Hilbert spaces. But there has to be a ultraviolet cutoff. And the ultraviolet cutoff is set in physical coordinates, not in co-moving coordinates. And therefore, to maintain a fixed physical ultraviolet cutoff in an expanding universe, you have to create modes. So this is extreme violation of unitarity. And so if we demand that this violation of non-unitarity does not influence the classical region, then we get the demand that no Trans-Planckian modes ever exit the Hubble horizon. So these are two sets of justifications for the TCC. Okay, and if you accept this, there are severe implications for inflation. So here's the space-time diagram of inflation. You have time, you have space. This is a standard diagram, which you already saw several times. This is a Planck length. This is the Hubble radius. And in this graph, I showed the TCC being marginally satisfied, namely the Trans-Planckian length at the beginning of inflation just hits the Hubble horizon at the end of inflation. So inflation cannot last any longer than I drew here. But now if inflation is supposed to be successful, then the current Hubble horizon has to originate from inside of the Hubble horizon at the beginning of inflation. Otherwise, there's no causal origin for the origin of fluctuations that we see. And as you see in this graph, I showed this second condition as also being marginally satisfied. So this second condition says that inflation has to last at least a certain number of e-foldings. So now you see that if you change the energy scale of inflation, you move the location of this curve. The higher the energy scale of inflation, the closer the Hubble horizon moves to the Planck length, and the harder it is to make these two criteria compatible. Low scale inflation, this curve moves out, and it is easier to satisfy inflation. So let's do a simple calculation. We demand that the Trans-Planckian censorship is satisfied. This implies this relation. T star is the beginning of inflation. TR is the end of inflation. Demanding that the current Hubble radius starts out inside the Hubble radius at the beginning of inflation leads to this condition. And I'll spare you the calculation, but making these two consistent leads you to the following upper bound on the energy scale of inflation. The energy scale of inflation is the fourth root of the potential. So 3 times 10 to the 9 GeV. Well, by LHC scales, this is high, but not by grand unification scales, not by string scale. And since it is this quantity which sets the amplitude of primordial gravitational waves, the amplitude of primordial gravitational waves is constrained to be minuscule. So any inflationary model which is consistent with a TCC predicts absolutely no gravitational waves. In contrast to what people usually say. People usually say, let's measure primordial gravitational waves using B-mode polarization, then we can verify the predictions of inflation. Nothing could be further than the truth. Alternatives to inflation typically predict larger amplitude of gravitational waves. than inflation. And if inflation is consistent with the TCC, then this is the bound on primordial gravitational waves. There are always going to be secondary gravitational waves created by the density perturbations at higher order perturbation theory, but they are going to be of the order smaller than something like 10 to the minus 5. Okay. So now if you want to still save slow roll inflation, in order to get sufficiently large cosmological perturbations, we need very, very slow rolling. And that means that the field can only roll over very, very small distances. And then we have an initial condition problem, a severe initial condition problem. So bad news for inflation. What about alternatives to inflation? So alternatives to inflation are completely consistent with the TCC. So here is the proof for bouncing cosmologies. This is the same space-time diagram that you saw before. Contracting phase, bounce, short bounce phase, expanding universe. And you see that fluctuations start out with a wavelength comparable to the wavelength they have today. So they never get close to this region of ignorance. So bouncing cosmologies are consistent with the TCC. Emergent cosmologies are also consistent with the TCC because the scale of fluctuations is, the wavelength of fluctuations is constant during this early phase. It is only the inflationary scenario which is severely constrained by the TCC, exactly by this mechanism of exponential expansion. Okay, so good. So now I would like to conclude. So I claim to have shown that inflation does not naturally emerge from superstring theory. Standard inflation is in conflict with the Trans-Planckian cosmic censorship conjecture. And even an inflationary model which is consistent with the TCC is highly fine-tuned. Alternatives to inflation are not in conflict with the TCC, and alternatives to inflation are much more likely to emerge from superstring theory. And here are a couple of slides for those of you who are working on superstring theory. If you take the ekpyrotic bounce is a phase of very slow contraction given by matter with this equation of state. W is pressure divided by energy density. This ekpyrotic scenario does as well as inflation for solving the horizon problem and similar problems. And it is obtained by a negative exponential potential. And negative exponential potentials are ubiquitous in string theory. And if we look at a negative exponential potential, this is the field evolution. And you can compute the slope of the potential, the second derivative, and p is a very small number. So you see that all the Swampland criteria are satisfied. So the ekpyrotic scenario, which is one example of a bouncing cosmology, I think the most promising one, is consistent with the Swampland criteria, it's consistent with the TCC. And okay, string gas cosmology is motivated by a stringy construction, and so it's obviously also consistent with both. So let me go back a couple of slides to here, and I want to stop here. So thanks.
Yes, so it's open to questions.
Shanky, can I ask
Yeah,
a couple
please,
of
please.
questions?
Yeah,
This
please.
is Sriram here.
Please.
Hi, Robert. Wonderful talk. Thank you. My question concerned, the Trans-Planckian problem was initially discussed in the context of black holes and Hawking radiation. What are the corresponding implications for Hawking radiation?
See, the mode conversion, which you do when you compute Hawking radiation, that's done outside of the horizon, outside of the black hole horizon. It's not done in the Trans-Planckian regime. So therefore you are safe.
So the issue is not emerging from the Planck region, but it is crossing the Hubble scale.
So the curvature of space-time at the points where you do the calculation is always very small compared to the Planck scale.
Okay. I had one more question. This concerned your comment about ekpyrotic scenarios. One of the concerns is that they are sourced by the entropy perturbation and they may remain large post bounce. Can you comment about that?
Yes, I can comment on that. Okay, good. So I'll show you a model of safe ekpyrosis. So the challenges for the ekpyrotic scenario, which are the ones that you just mentioned, are the ones in blue. How do we get a bounce? How do we obtain fluctuations without entropy fluctuations? And what about gravitational waves? So now there's been a change, and the change is you add one ingredient to the ekpyrotic scenario, namely an S-brane. That's something well motivated from string theory. It is a statement that once during ekpyrotic contraction, once the energy scale hits the string scale, a new tower of string states becomes massless, and you have to include them at a fixed time in the effective equation of motion, in the effective action. So this is the S-brane action. And if you do that, then you automatically get a bounce. You get a scaling invariant spectrum of curvature fluctuations via the adiabatic mode, and you get a scaling invariant spectrum of gravitational waves with a fairly large amplitude. And specifically, you get these consistency relations.
I understand. Thank you.
So but this is all work done this calendar year with Z-Way 1. And also there's a paper on reheating with Keshav. That's good.
I'll take a look at them, Robert. Thank you.
Okay.
So there is a question from, yeah, Urjit, please, go ahead.
Just wanted to, maybe it's a well-known issue, but the bouncing cosmology curves, where the Hubble, inverse Hubble kind of shrinks to a small value, yes, and then bounces outward. You get a large negative curvature of the scale factor in time. So that would contradict positive energy conjecture, right? P plus.
That's right. That's right. And so let's go back to this. Do I have anything else? Yep. Okay. So this is the action for the ekpyrotic scenario with an S-brane. And you see this term here, the S-brane term. This is like a topological defect rotated by 90 degrees in space-time. And a topological defect has vanishing pressure in orthogonal direction to the defect. Therefore, this term has zero energy density, and it has negative pressure because it has tension. Therefore, it automatically gives you the conditions that allow you a change from contraction to expansion.
Okay, thanks.
You see, this comes completely naturally. The delta H is related to the tension.
Okay.
Yeah, I have a question. So regarding the bounce, at the end of the bounce, basically there's going to be a large amount of perturbations which will be generated. So there could be a huge back reaction effect. So one of the concerns was that there is, will we get a scale invariant power spectrum? How does?
So the answer is yes. In the ekpyrotic scenario, you get a scale invariant spectrum of fluctuations. And now, if the bounce were to occur at the Planck density, then then you would have a huge sea of ultraviolet fluctuations. And then you would have a back reaction problem, the same back reaction problem as you mentioned. So if you want this to be under control, then you need the bounce scale, energy scale, to be slightly lower than the Planck scale. Typically about the gut scale would be good, which is about the heterotic string scale.
Okay, fine. There's one question from YouTube, so I'll ask that. So let us consider an inflation model which is consistent with TCC. Then how can we know from observation whether this model can be verified through observations, whether this is inflationary model, for instance?
I don't know the answer to that because I know how to disprove. So given any model, any concrete model that you propose that that satisfies the TCC, you will be able to disprove it if you find a spectrum of gravitational waves with an amplitude which is larger than the amplitude given by secondaries.
Okay. Okay. Vikram?
No, I had that same question about the observations.
Oh, okay.
Actually, another way is to go after the tensor spectrum, the slope of the tensor spectrum. So if you are fortunate to be able to measure the tensors,
okay,
you can measure the tensor spectrum. If you find a blue spectrum, you will have rolled out all inflation consistent with the energy conditions. That's an even stronger statement. Not just models consistent with the TCC.
Okay, so I remember there was a long back, I think Subir Sarkar had a model of inflation which is electroweak scale. I think it had other problems of nucleosynthesis, but I think Subir Sarkar, University of Oxford, this was in 2000s, I think he had a model of inflation during the electroweak scale.
Right. So unfortunately, I don't know that model, so I can't.
Okay, fine. Okay, fine. Okay. I think there's one more question from YouTube channel. Is string cosmology itself well accepted? That is, I think it's very subjective, so you can answer what.
Right, right. So, is it well accepted? The answer is no, it is not well accepted. See, but and one of the reasons is that we don't even know what non-perturbative string theory is. So until we really have a condition for real string cosmology, for string cosmology to be accepted, you will first need to have non-perturbative string theory. But what we can do is we can try to develop toy models of early universe cosmology based on fundamental principles of string theory. And then we can see if those models have interesting predictions. And I think this avenue of research is well motivated.
Okay. Yeah. Is there any other question?
Yeah. I have a question.
Yes, Manu, please.
Yeah. Professor Robert, thank you for the nice talk. There was a paper by David Vance in which he said that given a power spectrum and inflationary slow roll model that explains that power spectrum, there will always be a dual bounce model.
That's right.
If we have, and so my question is that if that inflationary model is not consistent with one of these, the Swampland, at least the Swampland argument, then what happens to the bounce case? Because there is a dual between those two, and both of them explain the data. Then how does it?
To my knowledge, the duality is at the level of the cosmological perturbations. it doesn't carry over to quantities like non-Gaussianities or gravitational waves.
Okay.
So I think there's a limitation of this. In addition, see, let me go back to this. So this is a setup of a bouncing cosmology. So at the level of adiabatic perturbations of the canonical field, the dual to exponential expansion is matter contraction. So it is a contracting phase which is matter dominated in this early phase. So that's the dual to inflation for the perturbations. Now the matter contraction is a repeller in initial condition space, whereas inflationary expansion is an attractor. Anisotropies blow up on you in the phase of contraction. I think the answer to your question is that this duality is a limited duality, and it has important caveats.
Shanki, can I ask a brief question? This is Sriram.
Yeah, please. Yeah.
Robert, do you have any models in mind for leading to, an epsilon of 10 power minus 30? Because the potential will hardly have any slope.
Yeah, my answer is no. But I don't have any models in mind, but I don't want to. This seems see, let me go forwards. I think it is more promising to develop alternatives to things. I think inevitably a model with such a small epsilon will be fine-tuned.
I have a question. So regarding the Swampland criteria, starting from effective field theory models constructed from string theory, can we make a generic statement of which models from given a string theory framework, which models can be ruled out? Is there a way of doing it?
Well, this so I would say models which violate these conditions are ruled out.
But these are all for the scalar sector, right?
Yes.
So, but I have to only consider the scalar sector of the model. Is that right, or is it just? But it can.
No, this is no. This isn't. These are criteria for the scalar sector. Now, for the particle physics sector, that's a completely different ballgame. So then the question is, what kind of compactifications can give you something like the standard model, or what effective field theories you could construct of fermions, gauge fields, and scalar fields are inconsistent with string theory? I don't know the answer to that. I've never looked into that.
Another question from the YouTube channel. If the value of the Hubble constant obtained by the Planck model of evolution of universe is wrong, what that go against inflation used in the model?
So I guess the question is about the Hubble tension.
I guess, yes.
Right, so I don't see a relation between early universe cosmology and the Hubble tension. So I think it's independent. I think the Hubble tension is a very interesting thing, and it may teach us something about fundamental physics. But it's not along the lines of the discussion I gave in this talk. I might refer you to a paper by Agarwal, Obied, and Wafa of, when was it? June 2019. where based on the swampland, where ideas of the swampland, they argued that the dark sector would have interactions between dark matter and dark energy, such that there would be a flow of energy from dark matter to dark energy. And that made predictions for the Hubble constant. So the answer is, in terms of what I discussed today, there's no connection with the Hubble tension, but that doesn't mean that there's no connection between fundamental physics and the Hubble tension.
Is there any other question?
Oh, I have a question.
Yes, Manu, please. Oh.
So, Professor Robert, when we look at the alternatives to inflation, we point out that they are free from these problems. But what was the reason that inflation gained more prominence in the beginning? There should be some problems with the bounce and the emergent universe theories also.
Well, see, inflation was the first early universe scenario which gave the criteria, with which the criteria of Peebles and Zunyaev-Zelovich could be satisfied. So it has priority for being the first. And then it is also the only model which is self-consistent at the level of effective field theory. So if you like effective field theories, it has an advantage. Bouncing cosmologies, you are not self-consistent. You need to have an extra ingredient. Okay. So they are more developed.
Mm-hmm. Sure, thank you.
Yeah, so if there are no more questions, let's thank Professor Brandenberger for a wonderful talk. I'll clap for everybody.
Thanks for listening.
Yes, okay. So people want to ask more questions can be in the Zoom room if they are interested to ask more questions. That will also be fine. Okay.